Now we jump to a special case of modulation or angle modulation, in which we consider when the message signal is a pure sinusoid, and we normally call that as sinusoidal or tone modulation. So we are assuming that the message signal can never take any other arbitrary form. It will only be a pure sinusoid. It might be a sine or a cosine, and for PM and FM respectively. And therefore, from the previous equations where we defined phi of t, we can say that phi of t is going to be given by b beta sine of omega m of t, which we said was equals to kpm of t. And therefore, it is at this stage that we are saying that message signal is pure sinusoid. Therefore, our message signal can be of am sine omega m of t. Therefore, when you replace this in this equation, we end up with beta being equivalent to am times kp, or purely that for P4 for PM or phase modulation. And that is what we have in equation 421. And similarly, for the FM, we were able to say that phi of t is directly related to kf times the integral of m of lambda d lambda. And since we were able to see this, if we know that our message signal is given by this, when you integrate this with respect to m, you're going to find that we are going to have d dt, we are going to end up with something that takes the shape of am over omega m. So when you now multiply, and we say that this is now equivalent to, of course, this now comes back to be cos omega m of t, and therefore we are equating this we are multiplying this one with kf, and we say that this is equivalent to phi of t, and therefore we can simply conclude that beta is equals to kf am over omega m, as we have seen defined in equation 421. This parameter beta m is known as the modulation index for angle modulation and is the mean maximum value of phase deviation for both PM and FM. And we also note that beta is defined only for sinusoidal modulation, do not be defined for non-sinusoidal modulation that is possible in real life. And therefore, we can say that beta can be expressed as change in omega, or which is the maximum change in the instantaneous frequency divided by the message, the angular frequency of the message. So we say that omega, change in omega is the maximum frequency deviation that we can experience when we are doing sinusoidal modulation. Now, to evaluate the spectrum of the sinusoidal modulated wave, we would perform some simple manipulations where we say that we replace equation 420 in our original equation, in which here we had phi of t. So we are saying that you replace phi of t with beta sine omega m of t. And if we are now, and we can say that now this is an angle modulated signal with sinusoidal modulation, and we can show that by the use of Fourier series that this signal can also be written in terms of Bessel function of the first kind, which can be viewed in appendix B of our text. And simply, this simply says that the our function x of t is a function of the Bessel function of the first kind with argument of order n, with the argument b, and n still comes at that stage of the equation. And there are some notable observations that we can capture from the functions of the Bessel function and this equation. So before we go very deep into the observations on the characteristics of the spectrum of the sinusoidal modulation, we should just have just brought in here the definition of the Bessel functions, and it simply comes up from the original equation that we normally use for when we are developing the Fourier series of a periodic wave. And therefore we are saying that when you put this term into we normally were saying that ej of theta, which is a function of t, and now we have seen that this one is now is a periodic wave. So when you put a sine wave in the exponent of this term, it gives you a series with the coefficient jn, which is defined as the Bessel function of the first kind of order n with argument beta. And of course, the other term remains as we normally you do with the Fourier series definition. Therefore, when we have that, we can also see that the coefficients of Jn that we are going to be using are defined here, and for the lower values for the higher values of n, the value of Jn goes to 0, and again for the argument beta, the higher the argument, the smaller the value of the Bessel function. So what we are simply saying, having introduced that concept, is that there's some observations that we can make regarding this equation, which is now a function of a Bessel function of the first kind. And the first one is that the spectrum consists of a carrier frequency component plus an infinite number of sideband components at frequencies defined by omega c plus or minus n omega m, where omega m is the frequency or the angular frequency of the message. And number two, the relative amplitude of the spectral lines depend on the value of beta, and as you have said, the values of the Bessel function of the first kind grows very small for the larger values of n. And number three, the number of significant spectral lines, that is having appreciable relative amplitude, is a function of the modulation index beta. And when beta is far much less than 1, then only J0 and J1 are significant. So the spectrum will consist of a carrier and two sideband lines. And when beta is far much bigger than 1, then there will be very many sideband lines. Then as we'll see in figure 4.2 down here, we see the amplitude spectra of argon-modulated signals having several values of beta, and here they are. So the smaller the value of beta, we only have two sidebands, one on the left and one on the right, and therefore as the beta increases, then you have very many sidebands developing, as illustrated on figure on figure 4.2.